Welcome back, everyone. This video or this session is about containers, the option type, and the result type. And before we begin, I would like to highlight that this is the very step that I'm going to take towards talking about abstraction, and a whole lot of discussion moving forward will be about how functional programming is different from imperative programming. That is when we think more and more in abstract terms. So, one of the key points that I'm going to discuss in this video is what are container types? Why do we need containers in our life? And a lot of functional programming is based on container types, actually, containers plus functions. So, before we start discussing what are container types, what I would like to do, which I've also done on the blog, is build an example. And with the help of that example, I would like to highlight, I would like to show, I would like to draw your attention to two completely different approaches of solving a problem. One problem is the imperative programmer's way. And again, I'm not saying imperative in a demeaning way, but it's a completely different approach. And the other is abstract thinking, where you deal with containers via functions. So the problem statement that we are trying to do, that I've taken an example in this example, is that imagine you work at a port and a ship arrives, and your job is to report the total number and total weight of all the apples that you have received, and move all the apples from the source container to a bigger target container. Make sure to throw out all the bad apples, that is, don't move just all the apples, move the good ones only. And once you are done with the movement, report the number and total weight of apples in the target container. So this is a repetitive thing: number and total weight in the source container, and number and total weight in the target container. Now this is a very typical imperative programmer's approach. Is open the source, and before you can start, you need your pen, paper, calculator, weighing machine, etc., etc., because you need to measure everything. So open the source and target containers, pick an apple from source container, add to count on the source side, measure weight and add to the total weight on the source side. If the apple is not bad, add to the count on target side, add to the total weight on the target side, put in the container, keep doing step 4 for all the apples in the source container. And this is somewhat, so instead of doing it with apples and containers, I have an input list here, which is of numbers. And instead of measuring the total weight of apples, I'm measuring the total of values, for example's sake. So we have an input side of list, we have an output side of list. Input is input, output is an empty list to start with. Input list total, which is we don't know what is the total weight slash count here. We don't know the same here. So before we start, we run a loop, and instead of measuring good apples and bad apples, we are saying in this list the good ones are which are divisible by 2. So we run through this entire list and check out each value, and in the output list we add the selected ones, which is this will be added, 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 and this and this and this and this and this will be ignored during the, this is a filtration process. And once we are done with the adding elements in the output list, we are running two loops. One is for the input list and we are adding the total value. Similarly, we run the loop for the output list and keep on accumulating the value for the output list total. And once everything is done, we print out all the 4 values, that the input has this count, input has this total, the output has this count, the output has this total. Now, let's go back to the blog, and here I'm trying to highlight some problems. And the problems that I'm trying to highlight here is the if you start appreciating these problems, if you have problems with these problems, you will naturally want more abstraction. So, what are the problems? The problem is that you were not in a position to solve this particular problem if you are not aware of how to open the source container, which is full of apples. This is where you're opening the source container. You are iterating, accessing each element in the source container, adding element in the target container, and so on and so forth. So you have an understanding of how to open the source side of story and the target side of story, which is point number one and two. How apples are placed in the container. So you know how to pick elements out of the container. This is how you pick elements from the source container, and this is how you add elements in the target container. You understand that. And yeah, so those are the other two aspects. The point that I'm making here is, which I will make over and over again and again over the course of many videos, is there is something called structural awareness when it comes to functional programming and abstraction. Structural awareness is when you understand the structure of something, the inner working of something, and without the inner working of the input list, which is happening here, and the internal working of the output list. Now I understand you haven't really created the list data structure yourself, but you know enough that this is how you have to deal with the input side of the story, and this is how you have to deal with the output side of the story. You understand all of that, and this is not the biggest of the examples. Oftentimes the understanding or the assumptions with which you write code, it goes way too deep. This is a silly example, as a matter of fact, but in a lot of business applications, the knowledge with which program is written, that knowledge is too rich to be discarded as unawareness of the structure of what you are dealing with. So, what I'm trying to propose here is that abstraction is your helping hand. So, instead of doing all of this yourself, as moving apples from here to there, you ask for somebody who understands that. You get a helping hand. You find somebody on the port who knows all of this. Where when you focus on what you need, count and weight, movement, and just defining the criteria, that how do how, how do you declare an apple is a bad apple. So your job was to count and weigh and make sure that the movement is happening, and then during the movement you define the criteria for selection of the good apples and the bad apples. While somebody who was aware of the structural issue, somebody who knows how to handle the containers and so on and so forth, that somebody is aware of how to open the container, close the container, place the apples from here, and pick apples from one side and put apples on the other side. And this is where container types and functions come into picture. Now, this is another example that I have quoted, which I'll talk about later. So before I do that, I'll show you another example, which is exactly the same effect, that you have an input and you are doing this much in order to produce this result, is written as a different example in F sharp altogether. Now, before we examine this uh, F sharp code, I would like to highlight that this is not the best way to do things in C sharp. You can use LINQ, etc., to write this entire thing in a much more effective, easier to write, read, maintain way. But that's not the goal right now. The goal is to highlight the thought process and approach difference between an imperative way of doing things versus the functional way of doing things. So here I begin with a list, just like here, and the input list total is this. Here I ran a loop to figure out the total values. Here I did just this much. Then my movement here is this. I am iterating over the input list and then adding elements in the output list. Here is my movement bit. And just like the input list total, here is the output list total. And once again, this is not a perfect example. This is not a comprehensive rich example to highlight or showcase all the aspects of this example or this problem statement. The goal here is to make you understand that my focus when I'm writing code like this is purely on what I need, not how to get what I need. This is all how to get what I need. This is all about what I need. So I have my input list, I have my output list. This is my input side container, this is my output side container. This is the total of the input side, this is the total of the output side. And then I'm printing the total number of elements in the input list, the total of those elements, the total number of elements on the output side, and the total of those values. And this is what abstraction is. Abstraction in F Sharp is a very, very, very simple idea. Realizing it is a tough thing, but it's container data types plus functions. Container data types exist because primitive data types are not, they don't hold enough information. An int can only hold an int, a string can only hold a string. A list on the other side can hold multiple numbers, an option, which we will talk about later today itself, and a result, or an async container, or a sequence container, or a computation container, etc. These containers can hold more information. And the functions that you use with containers are to make your life easy. You want to operate on containers with an abstraction layer. You don't want to deal with those containers as if you understand everything about those containers. Because if you understand everything about everything there is about those containers, there is no abstraction. So I'll quickly repeat myself. Abstraction is when you have containers which hold information. That information in most of the cases is more than what a raw primitive data type can hold. And then you have functions. And what you learn slowly and slowly eventually is what containers are useful for what, solving what problems, and what functions are useful for solving what problems. And eventually, as you have practiced and executed enough F Sharp projects, you develop that natural sense of, okay, here is a problem. I need this combination of container and functions. And that's all functional programming is about. Behind all the fancy words and keywords and buzzwords and mathematical ideology and category theory, at the end of the day, it all boils down to containers, functions, and transformations. There is just nothing else. So the evolution is to understand this and keep building on top of it. Okay. So I'll now show you another example. Don't be overwhelmed by this one. So this is the same problem statement, and this is the example that I have given on blog. I'll try to explain what I'm doing here. This is where I am mixing two concepts. One is I'm solving the problem via abstraction. I don't want to get into the structural awareness of the list and so on and so forth. At the same time, I wanted to highlight how this can happen in a pipeline manner. So I begin with this, and let me also make it slightly different as opposed to the example on the blog. Instead of this, I'll use this and I'll get rid of this. So here is the pipeline starts with an anonymous record. Recall, anonymous records are records without any formal type definition. So I'm creating a record out of thin air, which has these six fields. Source list, which is this. So I can actually even get rid of this declaration. Now we are dealing purely with a pipeline. This pipeline produces a result, and that result goes into after work, and then we are printing these four values based on what's in the after work. So we start with this anonymous record. This anonymous record says it essentially starts with an input list, the source list. The source count we don't know because we haven't done any computation yet. The source weight we don't know. Target list, I'm using list.empty because I need to tie up the data type. So remember, there are no nulls. Had it been C sharp, you would have said target list is of type int list or list of int, and the current value is null. No, you start with an empty list so that you have stitched the data types together. Target count is 0. We don't know the value today, right now. And target weight is 0. So now we need to figure out 5 things: the source count, the source weight. We need values in this target list. After filtering values from this, we need target count, we need target weight. And if you look carefully, 1, 2, 3, 4, 5. We need to figure out these 5 values, and we have these 5 functions in a pipeline in the form of lambda. So let's examine. Each lambda is the state of the operation before the lambda comes inside the lambda via variable st, which is short for state. So the state right now is this. After this step is done, the state is this. After this step is done, I can actually get rid of brackets. These are a little bit noisy. You don't need these brackets. I add these out of poor habit, so excuse me. So each stage has a state before it and after it. So this is the starting point. Here is your state. Here is your state. State changes, comes here. State changes, comes here. State changes, comes here. State changes, comes as the output of this function. So if you look at the data type of after work, it's nothing but the anonymous record itself. So we are just toying with the same anonymous record again and again in this pipeline. And you are not supposed to create pipelines where the entry point data type and the output data type is the same. It's just a coincidence that is happening in this example. Pipelines may start with an integer and may end with a task of int of list. It doesn't matter, as long as there is a sequential flow, there is a natural flow in the pipeline. So let's examine what I'm doing. So because this is a record, anonymous in this case, I'm using the update syntax. I'm doing st and I'm repeating the source count here, and I'm simply saying source list dot length is now the value goes into this. In the second stage, I'm calculating the sum of this list, which goes into this. Then I'm creating a target list by filtering. In the fourth stage, I'm finding the total element number of items in target list, which becomes the target count. And in the next stage, what I'm doing is calculating the total. And this stage and this stage, they are same, except this is operating on input side and this is operating on the output side. Similarly, this is operating on the output side, this is operating on the input side, and this is our moving apples from one container to other without bothering ourselves with the structural issues. And once you have your pipeline completed, the result is captured inside after work. What's left is to just print it. So this example and this example are the same things implemented in a different way. This is to highlight how to approach it functionally, solving it completely via abstraction without getting into structural issues. And this is because sooner or later we will start writing code or examining code and building complex things which are based on pipeline, because that's where the the fun is, where that's where the convenience and beauty of functional programming is. I just wanted to highlight this example. Okay, so study all the comments that I have placed. Now, I'll begin with the option container type. What is option container type? So container word is what I use. I often use this keyword, word, when I'm talking about abstraction in F sharp, when I'm writing about things in F sharp. So bear with me, because if you go to MSDN, you will not find the word container. Is the word I use. I use it for a very theoretical purpose, because when you study functional programming, and sooner or later you will study category theory, there you are dealing with elevations and so on and so forth, which I'll talk about perhaps in one of the next videos. So bear with me, spend some time over the blog and videos, and you will realize why I call these types container types as opposed to the option type. So option type is one of the most heavily used data types in F sharp, is your null replacement. So let's just draw our own fancy type called type data may be available of type T, which is a discriminated union. If there is data, you will say data of T, or no data, and that's it. That's what option is. So why do we need option type? Remember, in the beginning of this series I said absence of data has a better representation in functional languages in F sharp, and that's how you represent absence of data. You have a discriminated union which may have data, may not have data. If it has data, it is of type tick T, the generic type. And why have we created this as generic container? Because you may be dealing with cases where you are dealing with string data or the absence of string data, int data or the absence of int data. So how you use this? So let's take this example. We are saying let x equals to data 1. So then x becomes data may be available of type int. Okay, or you may say y equals no data. Now, if this seems as a replacement of nullable to you, then no. Nullable is similar, but it's not the same. I'll explain how this is different from nullable, but for the moment, let's just discuss the data may be available. Let z equals to data 1. So in this case, you are saying x has data of type integer, z has data of type string, y has no data. So the option type in F sharp is exactly this, and it has two cases. It has the sum case, which has it has something in it, or the none case, which is data is not available. So I have written some examples. Yes, there is data 1 int option. So you can write int option data type in two ways. You can say int option, or you can say option int. It's completely a matter of choice. Okay, so a is a sum case of 1, integer 1. B is a sum case of string 1. C is a none. I've also created a record type here, which is type person. A name is a string, and age, which if your application says, if the requirement of the application is, or the functional specification of the application is that age may or may not be known. Age is an optional field. When a user is submitting the form, age is not a mandatory field. So age then becomes an int option versus integer. So when you are creating a student record value, you're saying name is whatever in both the cases. In one case, you are saying age is someone, and in the other case, you are saying age is none. So age being age may or may not have data. So how do you achieve that flexibility? By dealing with int option. You can have option of anything. If there is a data type, that data type space option becomes a situational data placeholder. Okay. And again, these examples. And the another very commonly used data type in F sharp is result container. So let's first of all draw our own result container to see what is the result. So result container is for any operation that may fail. So I'll say not let type may fail equals to it worked, and the result, whenever you are executing an operation, it has some result. So it worked of t, or it failed of exn. So quickly, may fail is, it represents outcome of an operation, whether it was successful, it worked, and if it was successful, it will return a value of type tick t. In worst case, it will return unit if you are simulating an action in C sharp or a pure side effect, but shouldn't really do it often. And then it failed. Now, the problem over here, it failed, is that you are assuming that every time it fails with exception as the outcome. You are not leaving it flexible. So let's make it flexible and let's call it T error. That it is up to, when somebody is failing an operation, it's up to them whether they want to fail the operation with an integer as error codes, or with strings as messages, or with exceptions. So instead of using exn, we can use this. So now this becomes a super generic placeholder which holds successful or failed result of any operation. I mean, think of any operation. If the result of it can be captured in this container type, the answer is yes. So F sharp has a built-in container which has OK case of type tick t, and it has an error case of type t error. So may fail over here, replace may fail with result. It worked becomes OK, and it failed becomes error. So again, few examples here. And I forgot to show you the pattern matching, because these are nothing but discriminated unions. You know how to use pattern matching. So this A here is this sorry, int option. So that's how you do pattern matching on options. And on result, exactly, because it's a discriminated union, it's either in OK case with the answer, or in the error case with failure result. For an option, it's either in some case holding the data, or it's either in the none case when it has nothing. So that's how you create a result in OK case. This is an OK when you have an integer. This is an OK when you have a failure. Or you can actually do this for any data type. Right now, I am forcing an exception here. I am saying we are in error, and the error detail is an exception. You may end up writing this error, just a string, I ran into some problem, because the result type is not forcing you to use exceptions on the error side. This is an example of using exceptions on the error side. This is an example of using a string on the error side. This is an example of using an integer on the error side. That choice, that flexibility you have. And what should we have on the error side is a different discussion. We'll have it later. But the result type allows you to hold any data on the OK side, any data on the error side. So quickly repeating, option container is when you have optional presence of data. Data may or may not be available. When you have data, and if the type of data is tick T, you have the sum case. When you don't have data, it's none case. Result is for duality. It may go left or right, just like we did either OK of type tick T or error of type tick T error. And this is how you do pattern matching on options. This is how you do pattern matching on results. Now, at this moment, I am not discussing functions which are available for option and container data type. That will start a lengthy discussion in itself, so that's planned for later. Uh, I just wanted the intent of this discussion was to just to make you aware that moving forward, our goal is to slowly, gradually think more in terms of containers, and containers are not in isolation. Containers means there are containers and there are established functions for those containers. And then the moment you see a problem, the pattern matching in your brain tells you, okay, I'll solve this problem with this container and these set of functions. So this container and a function becomes a set of functions becomes a pattern in F sharp. So patterns and practices in F sharp are completely different from patterns and practices in C sharp, Java, whatever. There you have interfaces, abstract classes, and 20 other concepts and complex ways to stitch those. In the F sharp, you have container data types plus functions. In order to solve a set of problems, there are certain types and there are certain containers, and that's all patterns are there in F sharp. It's a completely different ideology altogether. So we will discuss more as we move on. Alright, I'll conclude this one. Thank you. See you later. Bye bye.